So I think we'll try to begin with my lecture. Welcome everyone. My name is Bartlomiej Chojnacki. I'm from Poland, from Mega-Acoustic company. I'm the leading acoustic research engineer there. It is my pleasure to open this part of the exhibition and fair of the lectures. I'm very impressed how the organizers are trying to bring together the manufacturers, attendants, and the scientists and educators, which I am as well. So I wanted to bring the topic of the room acoustic a little closer to also some kind of the manufacturer industry, because I think the room acoustic is kind of the exotic topic for most of us, and many people are not aware about why acoustics is so important. But actually, it's the knowledge is growing up very fast. Even current fair is presenting this, because now we have many rooms treated. Like a few years ago, it was just like 10% of the room, or even the stand exhibition stands treated with any acoustic panels. Now we have many of them, which I am very happy of, because it's still this is the most important part of our work, to let you know why you should invest in the acoustics. So it's also good time that we have today the trade day. So mainly we are meeting the dealers, the press officers, and it's even more important for you than the final customer to have the very good room acoustics in your showroom, because if you will introduce the good quality stuff, devices in your showroom to the customer with the good acoustics, it's the best performance you can achieve there. And of course, this is the higher chance that the customer will take the stuff home and finally maybe buy it, right? So even the final, the dealers should really take care about it. Here we have one of our realization with the Mega-Acoustic panels in audio equipment dealer in Poland, where the room is fully treated. Those guys really told me that after the treatment in the room, they feel another life of their salons, their dealing shop. So they start to sell more and more, and because in their room, stuff always sounds good. And then, of course, to be honest, there is another business purpose for this this kind of the treatment, because acoustics starts to be sometimes the kind of explanation for everything. Like, of course, it doesn't sound good in my room. Oh, because you have the poor acoustics, right? So, okay, you are the dealer, you are selling the equipment, you have the correct acoustic devices in your room, and there is no explanation there's a poor acoustic, because it sounds good, and okay, customer is taking it home, it sounds worse. Okay, man, you need the acoustic as well. So, good starting point for selling the acoustic panels as well. So, for the current lecture, what about us? We are the Polish leading acoustic treatment manufacturer, located somewhere there. This is our place in the Europe. We are very advanced in the acoustic foam processing, and for some years we are using also some CNC cutting machines and UV printing to achieve best quality fiberglass panels, which are a little more advanced than the standard foams, and of course the diffusers with the full range of the offers. And shortly about me, my place in this company, because I'm the acoustic research engineer, so usually I call myself the scientist. I try to be connected with all industrial and scientific environments, which keeps us like updated on any news around the world, both with the European Acoustic Association, with the Audio Engineering Society, when I have the pleasure to be the member of the Education Committee and chair on Europe International in ASSDA. And also, I'm trying to pursue for the PhD degree in acoustics in AGH University of Science and Technology in Krakow, in Poland. So for this lecture, I tried to very fast sweep from the basics of the room acoustics, because I want you and me to talk at least at some point with the common language, right? I want to have the full understanding of some topics I will cover today, and I hope it will take like 25 up to 30 minutes maximum, because the most important part here is these case studies and Q&A, because for the dealers, I won't make the acoustic engineers from you in half an hour. There is no doubt. And I won't even try, of course. So learning the basics and like looking how we can do this, how to answer the questions like the customers or anyone else will ask you for in the way like how does it works? Why should I do this? Is more important than like knowing how we manufacture this or what is the lowest part of the knowledge to like provide the self-made panels to fix the acoustics. So beginning with those basics I explained, in acoustics we can present some kind of the signal representation if in time on the frequency domain. So the time is basically the recording of the sound pressure or the voltage for the microphone in the time domain. It can look like this, a single sine wave. But considering the room acoustics, we usually don't use it. We prefer the frequency domain representation, which describes the energy in every frequency in the given signal. Of course, this is very, very easy, basic topic, so we have just one sine wave with one frequency. We have more complex tones, like bird singing, where are some more frequencies. It begins to look a little more complex. But of course, when we are talking about the music, so we are listening to anything, usually the spectrum looks rather like this. So we have the almost full frequency range with the many frequencies in the same time, complex tones, many instruments, and that's why it's closest to here. Why I'm talking about it? Because the technical data of the devices like the amplifiers, columns, it's quite obvious for everyone how does it look like. So we have the power, we have the frequency bandwidth, or the sensitivity, right? Everyone knows how does it look like and what does it mean. In acoustics, not really, because basic representation of the acoustic panels specification are some kind of the plots with the strange named coefficients like diffusion or absorption coefficients. But it's in the basic level, it's very easy to understand this. So it's the representation in the frequency band described in which frequency band the panel is working at which power. Let's simplify this to the power or the quality of the panel. Usually those coefficients are from the range from 0 to 1, so you can consider like in these frequency bands, this panel is not working, here is working perfectly, here is average, right? So basically, if you are searching for the acoustic panels, search for those plots, or just for any coefficient an acoustic manufacturer is providing, because if they are not providing any coefficients, so maybe they are not really aware about what they are doing, right? Any type of the coefficients is very important in acoustics. Like, you never will buy the columns or the amplifier without the knowledge about the power, right? So also don't do with the acoustic treatment devices. Going through to the acoustics, let's consider we have the studio monitor with the beautiful free-field response measured in an anechoic chamber. This is presented by the manufacturer. Oh, it's awesome, right? And I will have it in the room. Of course you won't. We have the room. Let's consider Carda's setup. This is not important now. You are putting this in the room, this kind of the response speaker, and you are receiving this. So it stops looking very impressive. It looks terrible. We have an influence of the standing waves, influence of the room first reflections, and yeah, some people are not aware about it, and yeah, that's why looking on this is totally not important in this case. So, and even this is kind of the good situation, because what you usually have rather this. This is the real characteristic. So you have very, very many notches, peaks, valleys, amplification, de-amplifications. It's never even. And you need to have the room acoustic to solve this. In the basic level, I divide every measurement, every project I'm developing to the two ways. So you have the wave acoustics and geometrical acoustics. There is a border in acoustics between them called Schroeder frequency, which means after this frequency, we can neglect some wave phenomenons in the rooms. Before this, we have the wave acoustics and the sound propagation described by the wave equation. After we have some kind of the geometrical acoustics and the optic type of the sound propagation, with more similar to the light propagation in the room. So like the beams with the Snell room considered as a main principle for the sound propagation, right? And why we need to divide this? Because on this plot, it looks like this. So here you have so-called room standing waves, room modes, room resonance frequencies, eigenfrequencies, 4 names for the same phenomenon, right? So here is this range, and after this you have the first reflection influence with some kind of effects of comb filtering. I will talk about it later, because first let's stick with the wave acoustics and the room modes. This is the first thing, and some people say even the only one you need to do in rooms. Of course, I do not sign this sentence. You need to take care about the full acoustic problems, not only the standing waves and the room modes, because it's always present. It's not looking, yeah, this is a very important statement now. So this is not working like this. Someone will tell you, okay, I have the good room acoustics without any treatment. You can have something okay, right, without very, very easy to notice troubles with room acoustics, right? But your room isn't faking the physics. If you have not treated first reflections, you always have them present. You can have some luck and set up the listening position with the speakers to the very, very, let's say, by the luck, usually, the good setup with the position of the speakers and the listening point, and have the small influence of the room modes. But it's never like, you know, always, if you have the non-treated room, you can only imagine how will it looks like if you will have it treated. Yeah, and you will never know what will be the difference until you try. Okay, so let's go back to the standing waves. The basics of this phenomenon, I like this GIF because it describes it quite well. We have 2 traveling waves, the green one in this side, the blue one is reflected from the wall. We can consider this as this room, right? I'm here, the sound source, I'm speaking to you, my sound, my voice is reflecting from the back wall and going back. In some given frequencies, in given points in the room, if you consider this axis as the length of the room, the waves are applying at each other, and we have amplification and de-amplification. And take a look on the red wave here. So basically you have in some points, you have all the time the nodes. So the 0 pressure points. In the worst case, you won't hear my voice. It will be like one frequency, and you will sit in the wrong place. If you consider this as the low frequencies, the bass, so you have the bass player playing, and you cannot hear some notes, for example, if it will be wrong place in the room, and it will be non-treated room. This is what basically the room modes are. So in the rooms, in the 2-dimensional space, it looks something like this. So you have the speakers, you have the listening points, and those blue areas is the very low pressure of the sound. So basically, on these lines, even you cannot hear anything for the given room frequency, which is dependent of the width, length, and the height of the room. Of course, it's quite easy to calculate, but I will talk about it later. So, of course, what is the main trouble here? That if you can see, those nodal lines are usually like in the middle on the axis of the rooms. And this is our main problem, because always you put the listening point on axis of the room, right? And that's why you are experiencing this very hard, boomy bass on some given frequencies. This is all about the room resonances. And you cannot avoid this. To find the best point is something like this, in these frequencies. So you don't see it in the red area, which is also bad. This is the amplification. The blue area is totally de-amplification, so 0 pressure. So sitting in the green zone or yellow zone is best, right? But you can do this in this case for this frequency, but then you experience all the time the troubles with the other. So this is why those frequencies will be okay, those will be terrible. So one short question. This is calculated by our acoustic calculator. It's in Polish so far, but it's quite easy. I think everyone will be able to use it. I will show it also later. And of course, you can also use some basic math calculation and the transformation to calculate the rooms for your own room. Simplify, you just need to take the wave equation, make some preparation for the plane wave equation, consider some sound intensity problems, and make some more maths to achieve. Yeah, sure, right? Just don't. Yeah, just don't, guys, because there is no need for this. Why I'm talking about? I was on one of our advertisement videos in Mega-Acoustic. I was deriving the full solution for the wave equation, and it took about 25 minutes to derive this, right? So just don't. This is the final solution, but don't. You can use the calculators, which works correctly for the rectangular rooms. This is not the only one calculator. Yeah, I recommend this because I know it's good, because I made it. So, but what are the problems present now on the slide? So this works only correctly for the rectangular and empty, fully reflective rooms. So take a look. If you put the furniture there, you put the columns, you put some screens, whatever, and it stops look so plain. It does not look so ideal. Take this. You should have here the red, 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 and red, right? In every corner. Corners are very, very supposed to be the problem with the problematic points of the generation of standing waves. But because of the furniture, they're a little tangled, curved, and that's why, basically, to be fully sure about what kind of the frequency modes you experience in your rooms, you need to measure this. There is no other points. But, of course, the starting to calculate is very, very good starting point, and you can calculate it like with 5 to 10 hertz of the accuracy, and most of the bass traps would be able to tune to those frequencies you will calculate. Because, of course, there are more troubles, because usually, maybe not the showrooms, the standard rooms, when we are listening to music, looks totally strange. It can be in many different ways treated and shaped, and then the modes looks even worse. So it's also described on our site if you would like to take a look on this. But basically, what you need to be aware of, the corners are always problematic. So this is good kind of the blind shot. If you even don't know much about the acoustics, can't make the measurements, you can even try to listen to some hard bass music and try to go into the corners and listen to if the bass there is more bass inside. If there is, this means this is the room mode generation point. Just put the bass traps there, right? And of course, very popular rooms with the curves, like the cut roofs, and then even the corners on these joints between the ceiling and the curve is very, very problematic usually. And very standard, this is kind of the jump, so L-shaped room with the curves on the one side. Also, take a look how the maximum pressure zones are like extended in this side, right? So also there is a very important thing about how the materials, whatever the materials put in the interior. So modern interiors are full of the glass, for the open spaces. Like this is one big room, right? And it's getting more problematic. We can calculate with so-called FEM, so finite elements methods for calculation the room eigenfrequencies, but it's more complicated. And those windows have great influence of the room modes, and even, of course, for the pressure distribution in the room. So it starts to look rather like this. So here we have something totally not accurate for the rectangular room equations. So what's the solution? So basically, just put the bass traps in the corners, in the problematic places. Usually the corners are like kind of the blind shot. In the treated rooms, you can see in the corners like fully covered with the bass traps. You can use broadband bass traps or tuned resonators for the given frequencies. The frequency, also in this case, is just put it in every corner. Or as you can see, or how many you can see put there, because you know the WAF factors, or how many you are able to buy, like just 2 is still more than nothing, right? And the bass traps can have different frequency characteristics. For example, the tuned are usually prepared for one frequency to absorb it very much, and the other less. The broadband have the full frequency range to absorb. Which is better? Of course, I can say this one is usually safe, because especially if you can't calculate correctly which frequencies are problematic. To use the tuned bass traps, you need to be aware which frequency is wrong here, which is the resonant to order these tuned bass traps, right? So this is very safe, but of course, the negative of this is that even those bass traps are 40 centimeters in the edge length, right? So pretty big. Those are 25, smaller. But those, even they are quite big, we won't make bigger because no one will use this. But come on, 40 centimeters is big enough, right? And see that the frequency absorption, the sound absorption coefficient is dropping down around 63, so basically it stops working under 50, and we won't force it to work further. So if you want like have the absorb the lower frequencies, like under 50 hertz, you can't use anything else than the tuned bass traps, right? So I think we will stop for now with the low frequencies. Let's go for the geometrical acoustics. And here is one tip from me when I'm usually considering this border between the wave and geometrical acoustics. Because if you will calculate the room frequency modes, you can calculate some lowest, but you can calculate like everything for the very high frequencies. You don't need to do this because of this border. I usually assume it around 200 hertz. It's dependent to the volume of the room and the reverberation time, but yeah, let's say above the 200 hertz, there is no problem with the room modes. So above this border, you are considering the rate type of the acoustics. And how does it look like? Let's go further with our calculator, which is returning you these beautiful plots. As I said, in the higher frequency range, you are using the kind of the light type of the propagation for the sound. So the angle of the incidence is equal to the angle of the reflections. You can take a look. So if you put the speakers in the room and the listening point, so basically on every wall you have some points, which is the equal angle of the incident wave and the reflected wave, which is called first reflection point. And you need to treat it correctly to avoid the sound amplification and de-amplification. So this is basic case, if you will consider just the first reflections, but yeah, in the real situation sometimes can look like this, yeah. And here makes the trouble. It's all dependent what kind of the room it is. If it's very, very sterile, like the studio, or very, very very accurate mastering studio, you need to care about more of them. But we are talking about the hi-fi listening rooms. And usually they are the showrooms when you need the space for the stuff, right? Or living rooms in customers' homes, right? So yeah, let's stay with this. Even if you will treat with single panels, each of those points, you will experience how huge amplification in the experience of the perception of the sound will be. You know, to be honest, we don't have the not happy and not the customers which are angry after buying our panels. They can be angry after we make the presentation, and then they notice how much they need the acoustic panels, because they need to encourage the wife, to invest some money and move some furnitures to achieve better acoustics because they start to be aware how important it is. Yeah, this is our calculator, which I recommend you from also for one good feature, because I think this is the only calculator in the internet for the first reflections, which allows you to use the non-symmetric room configuration. So for example, you can do something like this. This is a very common situation in the living room, right? So you have here you have the kitchen or something, and here you are putting the speakers, you have the listening point. None of the calculators I found in the internet can use it, yeah?
I think there is another one, but
Yeah, okay, thanks. Yeah, but anyway, there's another one, so maybe there are just two, so still, this is quite good feature, I think. Yeah, okay, so why the first reflections are problematic? Here I have another very nice GIF. How does it look like if you have the one sound wave incoming, and then let's say this impulse, and another like delayed in the time domain, right? This is exactly what the reflection is. You have the direct sound approaching to you from my side, and the reflection from the wall, right? And it's delayed. It's the same sound, just delayed a little bit in the time domain. And take a look. From the first point, it looks like the refresh. The first impulse have the plain frequency characteristics. If the second is growing, so the reflection is coming, it's become to be more and more amplified, de-amplified, and of course those values are even able to calculate because it corresponds with the time difference between those two impulses, right? For the more advanced acoustic calculation, we can even very accuracy with a high accuracy say which reflection is which basing on the impulse response measurement. And this is the phenomenon called comp filtering, and it occurs in every room. That's what I said, you know, even if someone will say we have good acoustics, so when you don't have the floor, you don't have the ceiling, you know, the floor and the ceiling are usually the toughest thing, very hard to treat. But anyway, it's present, right? And it looks like this. Here you have those valleys caused by the comp filtering, by the first reflections overlaying in the spot with direct sound. How to treat them? So basically, calculation of those points is easy. Many tools for this in the internet. And simply, you just need to put some wall panels for those points. Which is best? The best possible, the best frequency range we can achieve. So basically, if we consider we need to treat the first reflection from about 150 Hertz, you should have the fully absorptive panel in the 150 Hertz and everything above, right? To make it totally clear. Even this is nonsense to save the money on treating there. Even someone will say you, okay, you don't need the absorption from this frequency or upper this frequency. Those are just 2 or 4 panels, right? 1, 2, 3, 4, and usually those in some rooms those 2 points lie close together, and you can like solve this with one panel, like 60 centimeters of the width, right? And it's quite easy to do, but some points when I have the questions, okay, why you recommend those absorbing panels? Won't I over attenuate my room? I can say you won't, because take a look, just 4 panels, right? So it should be like 2 per 3 meters room to attenuate hard this kind of the room with the just 3 or 4 panels, right? So it's totally safe. So the important thing, you need to be aware about it. So for example, the diffusers usually in opposite to absorbers have the little limited frequency range they are working on. So you need to have the absorption and diffusion coefficients in the frequency band you want to have the first reflection treated. For example, if you have, let's say, here is 300 Hertz, we have the very strong comp filtering in this area, and you will try to treat the first reflections with this panel, it cannot work so correctly because it does not have the acoustic properties in this frequency range. It will like clarify most things from the 500 Hertz, but below it will be the problems, right? With those panels are a little more broadband. That's why for the very strong first reflections, I always recommend absorbers. I know that there are some purists and the hi-fi maniacs will say, no, absorption is bad, we need to diffuse the sound. Of course, diffusion is awesome, but we need to be aware about the limitation of the diffusers and the narrow band working frequencies. Last thing I wanted to cover from the basics of my presentation, the reverberation. Reverberation is some kind of the amount of energy you are storing in your room because of the late reflections, right? We call it decay time, and usually in not treated rooms, totally empty, it looks like this, so it's quite high. The problem is we cannot, we have some standards, like EBU tech standard for the broadcasting for the studios, from the stereo studios, but it does not correspond very well with the hi-fi resync rooms. When I'm designing the acoustics, I never try to tell the customer, okay, man, now you need to have the 0.25 seconds of the reverberation time, because it's totally non-objective parameter. For example, I like to listen to in a little higher reverberation time, but you need to be aware that the reverberation curve, so the curve around the frequency, need to be kind of flat. This is very important. It needs to be flat, and it cannot be too high, because then it starts to be acoustic fault. You can use it like, it can be here, the flat line here, or if someone wants to like the stereo studio conditions, it can be even this line, right? But it needs to be plain, like not totally amplified in many frequencies, because any kind of the non-linearity in acoustics is bad. And treating with the panels is very easy to decrease the reverberation in the room. I think I will little make it faster. This is not really important now, because the important thing is here that if you are applying the acoustic panels, of course, you are, for example, you are treating the first reflections, and you are also decreasing the reverberation time, right? So you need to be aware that to not use too many absorbing panels, and of course, you need to be aware about the frequency characteristics to avoid this, what we call the sound, the room over attenuation. If you will over attenuate the room, you won't like it, definitely. Of course, some changes are very okay. For example, those are so-called active acoustic roller banners. If you can have the pilot to move them up and down, and try to adjust the acoustics according to your mood or whatever. For example, in this case, I was designing this from the very nice treated room, kind of the live room, and for those roller banners, I could make, this like smoked jazz club with the very, very mild and characteristics, right? It's awesome in the purpose for the active acoustic banners, but yeah, it still depends what your customer will like. Of course, you won't know. That's why we have the standards, and you won't make it like blind shot objective. Okay, I will give you the jazz club, and you will be happy, because we have no idea if he will be, right? So you need to try to keep it plain first. And the most common thing in small rooms is this type of the curve. Because you have the furniture, you have some wall curtains, the window curtains, which is absorbing mainly mid and high frequencies, right? But they're not touching the low frequencies, and it happens like this. It's very easy audible. If I would show it to you, even in this room, I think we can little experience this. Maybe I have quite, you hear? I have quite high and mid-frequency voice. And by using the electroacoustic system, you are hearing a lot of the low frequencies here, because I provide more energy, and my voice sounds much more lower, right? Because, yeah, we don't have the bass traps here. It's quite obvious in the conference rooms, right? But still, for the important thing is here, you need to be aware of the characteristics of the panels. For example, the one panel is quite new in our offer, provided by Architected Sound, which we are dealer around the Europe, is OptiD, which is some kind of the slat absorber with the characteristics, for example, like this blue curve. So it's absorbing only low frequencies do not touch the high frequencies. And this is the result of the adaptation using the OptiD panel, right? So you are running out of this, going for this level, right? And it's awesome. This is like the solution for half the problems in the rooms, but you need to be, of course, aware about it. So we are, I think, in the end of these basics. I think I'm on the good time. So it's one of the rooms full treated. So you have the bass traps, foam, broadband, very accurate there. Reversion time is okay. First reflection, absorbing panels, but I used many absorbing panels there because, you know, this is the showroom for the dealer. In a hi-fi listening room, you usually have one sweet spot. In showrooms for the dealers, it's not so obvious. For example, you have like meetings or 10 or 20 customers at the same time on the presentation. You need to put them somewhere, and you need to have the bigger amount of the room treated for this. That's why I use many absorbing panels there, but then it blocked me to use more absorbing panels on the front wall. I don't like diffusers on the front wall. I try to avoid them, but I need to treat this wall. I couldn't use the absorbers, so I used the diffusers, right? Because those reflections on the front wall are usually weaker. Those are very strong, usually very strong. So I use the absorbers, then diffuser on the front wall, and it looks like quite correctly. Also, the reverberation were well treated, keeping very, very good characteristics on the whole room. So also we are trying to basically, let's say, teach people how to listen to the music, organizing some events to compare. Last time on the audio video show in Warsaw, we organized 2 rooms, one not treated, second fully treated, you know, and make some surveys around the people with the how they feel like. With, of course, the sound playing system was the same. It's the results, of course, it wasn't surprising for me, but it was like 90% for, of course, this is totally something totally different. And okay, this is the part of the definition, my main part. I will try to skip from some very important questions, because at some point I realized that it is impossible to make the lecture from the room acoustics like covering everything. Because yeah, I won't make the room the acoustic engineers from you. So I explain you also some like basic features. I receive the questions from the customers or the students when I'm teaching on the university. For example, can I fix my room with these 10 euro per panels foams? It's cheap. I want to do this. The answer is yes, of course you can, but the depth of the acoustic absorber is very, very important for the absorption coefficients. Take this, if you will compare the 6 centimeters, the same absorber, with the 10 centimeters, let's say in the 200 hertz, 0.3 absorption coefficient versus 0.6, right? It's 2 times more effective. And you know, that's why there's the very, very bad feeling about the acoustic foams on the market. Because people, usually the foams are even like cut into some fancy pyramid styles, right? And people are using them, and they think that will solve a lot of the problems with the room acoustic. It won't. It's good for some purposes, but for the first reflection, for example, you need best panel you can provide, right? So it needs to be tough. 10 centimeters is kind of the standard. And of course, you don't need more than 10 centimeters usually. Of course, like 15, it's totally maximum, because as you can see in 200 hertz, as I said about the frequency ranges for the wave and the geometrical acoustics, above this is the kind of the border for the shredder frequency, right? So under this frequency, you don't need to take care about the wall panels, because there are no problems with first reflection like in 100 hertz. So you don't need to have the very high frequency, high absorption coefficient in 100 hertz on wall panels, right? Let's go further. So this is very common. So is the acoustic foam better than the fiberglass? So the answer is no. They are very similar. You can take a look on this plot when I made the calculation. So the quality of the acoustic material is described by so-called flow resistivity. and it's measured for many acoustic materials, and the answer is the good acoustic foam. For example, our foams we are using have the flow resistivity of about 28 to 30 Ks every part. The good fiberglass have around 30 to 40 Ks of this beautiful unit, some PA multiplied by S for the square meter, right? And this is how those materials, let's consider this is the acoustic foam and fiberglass. They're very similar. And of course, some audiophiles will try to argue that, of course, but in the high frequencies, it's like 10% difference. Acoustic foam here is better or something. So comparing those plots in the practical use, they will be really almost the same. So, but take care about that. We are talking about the acoustic foam, because foam can be present in different types. You can have the furniture foam, you have which have the closed cells and have the flow resistivity of about 5,000. So then I agree, it's terrible. But yeah, the clue is to buy the panels from the acoustic foam, of course. Difference between the diffusion and absorption is the topic I started already a little bit to talk about, for example, in the terms of the frequency ranges, right? If you have the acoustic panels, I'm very sorry for the Polish axis here, but I think you should be already aware about the numbers here. So the diffusion is great because you are not using acoustic energy in a room. It's very important. So basically, and the diffusers are also safe. You cannot bad treat your room with the diffusers. Absorbers are quite dangerous if you use too many of them, or even if you will use weak absorbers. But diffusers are safe, so this is a very good acoustic solution. It's adding the additional small reflections, which are called diffused reflections, is increasing the spatialness of the sound in the room, and you feel like in a very well diffused room, you feel like covered with the sound around. But also, I think it's important to say diffusers are almost like to achieve the diffusion with the same size of the panel, you need to pay something like 6 times more, because the diffusers are also expensive. And the main problem here is the narrow band of working panel. So you cannot use it like to fully treat your room. With absorption, it's much more easier. So you need to be wise using them. So then there is a question, where should I put the diffusers? It's a very important thing, which I try to fight around the internet, around the lectures I'm leading, because when I see, those big skyline diffusers on the front wall, like covering half of this wall, even just imagine how expensive are those diffusers. Usually something like over 10,000 euros each, and this is the worst place you can place it. I have a special place for the special plot for this, because the efficiency of the diffuser is very fragile for the incidence wall angle. So for example, you have let's consider this situation. The best place for the diffusers are the back walls, because if I'm talking now to the back wall of this room and you put the diffusers there, we have the 0-degree angle of the incidence wave there, right? And it's working almost on the, let's say, full power, right? In my situation, if it will be put on the first reflection somewhere there, it will be like 45 degrees, 40, 30. So take a look on this. It's like almost 50%. And the same is if I will put it on the back, on the front wall. If I would be the speaker, I would be the sound source, right, the column, and I will stand here, have the pretty big diffuser on the front wall. It will be the angle like, I don't know, 70? Let's say 70, so that's curve. So it's like 15%. So you need to be very fragile. Here, diffusers. Here, okay, in the first reflection points on the front wall, it's okay, but not directly between the speakers. It usually can affect like second row of a reflection or something like this, but never, it shouldn't be the first thing you are doing in a room. And yeah, this is kind of the waste of the money. You can take a look, for example, on this slide, why I'm talking about the angle of the where on incidence wave toward the diffuser. You can take a look. Those stands are a little curved. They are not like totally parallel to the wall. They're curved to the speaker, to the outside, to reduce this effect of the high angle for the incidence wave on the diffuser. I did this on the purpose to also then, of course, use this slide on some presentations, but it's very important because just by curving this diffuser, I increase its efficiency by 20 or 30%, right? I can do this on a show, of course, but in the home it will be a little more it will be hard to curve the wall, but you need to be aware about it. And the diffusers placed on the front wall are, as I said, in this situation, saved me from over-attenuating the wall, the room. It's very important in some cases. But okay, here we have the front wall, and here is the back wall. So still I kept this, what I just said, back wall with the diffusers. You know, there was in front of this wall was what I told you in the showrooms. So we have the sweet spot, and behind the sweet spot some blank space for the bigger audience. It's very common in the showrooms. So people entered the showroom, like 5 or 6 guys, and was very close to the diffuser, totally covered by the sound, and it works very good in this room. So I think one of the last questions here will be, is better to use less stronger panels or more weaker? So the answer is, of course, I already covered this, to use more stronger panels than some weakers, because this is the effect of the over-attenuating the room. If you use some very low, like this, 2 centimeters full foams, you will over-attenuate the room, keeping the low frequencies non-treated. It's terrible. Don't do this, especially in high-field listening rooms. And so there are some purposes to do this. For example, in like office spaces, the call centers or something like this kind of the rooms, because then you need to like treat some other, like the acoustic faults, like the flutter echo or something. And it's totally no need to do this in the high-field listening rooms. I think last question here. So about the diffusers, usually you meet these numbers, and I do not recommend to look at them until you see the plots of the measurement, because of course this is totally no way to achieve this, because in the diffusers there are some rules to design them. My master thesis and also the bachelor thesis was supervised by one of the best specialists in the diffusers type in Poland and also around the world. And last time he derived some equations how to predict, because the diffusers are also absorbing because of the shape and some acoustic phenomena on the surface of the diffusers. There is the very important thing that don't use diffusers with the depth to well ratio higher than 5. So, for example, you will have our diffusers do not exceed this, because we know that diffusers with this ratio over 5 are very strongly absorbing, which absorbs cannot diffuse. And then, for example, our diffusers have 10 centimeters of depth with the well width of 2 centimeters. So this is the border, right? And if you see the diffuser of depth 30 centimeters with the well width, what is the ratio? 30. A little exceeded, right? So don't do this at home. Don't. Because those diffusers are very expensive, and yeah, it is kind of the waste of the money. They are just enjoying the eyesight there. And if you want very broadband diffuser, you can use some kind of the so-called fractal diffusers. So basically, it's the diffuser inside the diffuser, right? So you have the one diffuser with this well depth, and on the wells, you have another diffuser sticked to increase in the high frequency range the diffusion of the panel. This is good design because you don't risk the absorption in this type of the diffusing panels. Okay, I think this is the last question. So, very popular hybrid panels. So something which is diffusive and reflective in the same time. It's impossible. Which diffuse cannot absorb in the opposite way. Because just imagine, if something is absorbing like 80% of the energy, how can it reflect diffused another 90? Maybe okay. Maybe it's like the speakers put behind the panels, but you can sometimes meet this kind of the plot. So this is absorption, this is diffusion, right? We have 90% of absorbed and 80 diffused. No way. Absorbing panels works like this: that in given frequency ranges it can absorb, and the other can diffuse. Like going back to OptiD, it's absorbing here and diffusing up from 1K. This is real, because here is not absorbing, so it can diffuse, right? And you need to be aware about it if like someone is diffusing or absorbing? Oh, both, of course it is. It's very easy. Okay, I think I'm almost on my time, so you are encouraged to have some questions to me until I think like 5 minutes can be brought to for you. And yeah, any questions?